This lecture is about electric plasma rockets and VESTA and Ceres. NASA Jet Propulsion Laboratory is using a new type of engine to travel into space. It's called an electric plasma engine, or plasma engine for short. The plasma engine will soon replace current chemical engines. This plasma engine is highly efficient. And this is important to remember, a plasma engine uses only 1/10 of the fuel that a chemical rocket would use. The new plasma engine was chosen because new space missions are looking to explore the outer planets and asteroids in our solar system, and in order to explore these places, traditional rocket engines could not reach them. In particular, NASA's Dawn space probe is reaching beyond the orbit of Mars toward the asteroid belt. In the asteroid belt, Dawn space probe wants to study two asteroids named VESTA and Ceres. What is an asteroid? An asteroid is a large rock in outer space. Some, like Ceres, can be very large, while others can be as small as a grain of sand. Due to their small size, asteroids do not have the gravity to pull themselves into the shape of a ball. Asteroids are leftover material from the formation of the solar system. Astronomers group asteroids into different categories based on the way they reflect light. A large asteroid, like VESTA and Ceres, reflects sunlight because of their large size. The asteroid belt is located between Mars and Jupiter. These are not only large asteroids, but they are also called protoplanets. And this is important to remember. At one time, both Ceres and VESTA were classified as planets, but have since been downgraded to protoplanets. For some reason, these large asteroids never formed into planets like the planets in our solar system. Some believe that because of Jupiter's strong gravity, many of the asteroids never made it into a planet. Dawn's mission is to study in detail two of these largest protoplanets that have remained intact since their formation. Dawn left the Earth on September 2007. Electric plasma engines are quickly becoming the best option for sending probes to far-off targets. Recent successes made possible by electric propulsion include a visit by NASA's Deep Space One vehicle to a comet, a bonus journey that was made possible by the propellant that was left over after the spacecraft had achieved its primary goal. Deep Space One spacecraft flew over the asteroid Braille about 26 kilometers above its surface, which is about as high as a jet plane flies over the Earth. During the close flyby, the spacecraft took images, measured such basic physical principles as the asteroid and its mineral composition, size, shape, and brightness, and it searched for changes in the solar wind as it interacted with the asteroid to investigate whether it had a magnetic field. Plasma engines have also provided propulsion for an attempted landing on an asteroid by a Japanese probe, as well as a trip to the moon by the European Space Agency's Smart 1 spacecraft. In light of the technology's demonstrated advantages, deep space mission planners in the US, Europe, and Japan are opting to employ plasma engines in future missions that will explore the outer planets. Although plasma engines are only now making their way into long-range spacecraft, the technology has been under development for some time. As early as the first decade of the 20th century, rocket pioneers speculated that using electricity to power a spacecraft would be a good way to travel. The late Ernest Staudinger, a member of Wernher von Braun's legendary team of German rocket scientists, spearheaded the U.S. space program, and he finally turned the concept into practical technology in the mid-1950s. A few years later, engineers at NASA's Glenn Research Center built the first operating electric plasma rocket. That engine made its first flight in 1964. It worked for a half hour before the craft fell back to Earth. The benefits of plasma engines become most striking in light of the drawbacks of conventional rockets. When people imagine a rocket streaking through the dark toward a distant planet, they usually envision a trail of long, fiery plume coming from its nozzles. Yet, the truth is altogether different. Expeditions to the outer solar system have been mostly rocketless affairs, because most of the fuel is typically used in the first few minutes of the operation, leaving the spacecraft to float the rest of the way toward its goal. True, chemical rockets do launch all spacecraft from the Earth's surface and can make mid-course corrections, but they are impractical for powering deep space explorations because they would require huge quantities of fuel, too much and too expensive to be lifted into orbit. You should also remember that placing a pound of anything into Earth's orbit costs as much as $10,000. To achieve the necessary trajectories and high speeds for the lengthy race missions, many traditional probes with chemical engines have had to spend time, often years, going out of their way to planets or moons to slingshot around them. In doing so, these probes are able to gain the necessary speed to travel to the desired direction. Unfortunately, such out-of-the-way flight paths limit missions to relatively small launch windows, only blasting off within a short time frame to ensure that a precision slingshot around the planet can occur. Even worse, after years of travel to its destination, a vehicle with a chemical rocket engine typically does not have fuel left for braking. Such a probe would need the ability to fire its rocket engine so it could slow down enough to achieve the orbit around its target. Indeed, after a trip of more than 9 years, New Horizons, a chemical rocket launched in 2006, will only get a brief encounter of not more than a single Earth day with the demoted planet Pluto. For those who wonder why engineers have been unable to come up with ways to send enough chemical fuel into space to avoid such difficulties of long missions, let me talk about the hurdles. The explanation comes from what we call the rocket equation, a formula that is used by mission planners to calculate the massive propellant required for a given mission. Science refers to this incremental increase as delta V. Delta V is how much velocity that results from the exhaust ejection. In other words, the equation relates the mass of the propellant required by the rocket to carry out its mission in outer space. It looks at the velocity at which the rocket's exhaust will be ejected from the rocket and the mission's delta V, how much of the vehicle's velocity will increase as a result of the exhaust ejection. The delta V can be thought of as a price tag of the mission, because of the cost of conducting a mission into space is based upon the cost of launching the needed propellant. Conventional chemical rockets achieve only low exhaust velocities, 3 to 4 kilometers per second. This can be a problem because the fuel needed for the high delta V required for deep space missions would take up almost all of the weight in the spacecraft, leaving little room for anything else. For example, a travel from Earth to Mars would require that more than 2/3 of the spacecraft's mass be propellant to carry out such a journey. For longer trips, such as expeditions to outer space, chemical rockets would need to be more than 98% fuel. This leaves little space or little room for payloads and other hardware. As probes journey farther into the solar system, chemical rockets become useless. It's important to remember that chemical engines use up much of their space with fuel, leaving little room for anything else. Electric plasma engines, in contrast, offer much greater exhaust speeds. Instead of burning chemicals to generate thrust, the plasma engine accelerates plasma, clouds of electrically charged atoms or molecules, to very high velocities. A plasma is produced by an electric current or energy to a gas. There are 4 main forms of electric energy used in plasma engines. 1, laser energy. 2, microwave energy, 3, nuclear energy, 4, solar energy. The extra energy liberates electrons from the atoms of the gas, accelerating plasma clouds to very high velocities. In plasma engines, electric power for creating and accelerating the plasmas typically come from solar panels that collect energy from the sun, but deep space missions going past Mars must rely on other power sources, such as nuclear, because solar energy gets too weak at long distances from the sun. In any case, plasma rocket engines get up to speed more slowly than conventional rockets, and yet what has been called the slower but faster paradox, they very often reach higher speeds as they travel further through space. You should try to remember that in space there is no friction to slow down a rocket. It simply needs a small push from a plasma engine to gain speed. For example, a trip to Titan's surface would offer researchers a rare chance to search for the signs of chemicals that are the precursors to life. The mission would be impossible with a chemical engine. And with no in-course propulsion, the journey would require multiple planetary gravity assist, or slingshots, adding more than 3 years to the total trip time. A probe fitted with a little plasma engine would be able to do the job in a significantly shorter period of time, thus saving time and money. Today, there are 3 kinds of plasma engine rockets. 1 is the ion drive, 2, the Hall thruster, and 3, the MPDT, or magnetic plasma dynamic thruster. The ion engine uses xenon gas that flows through an ionized chamber where electricity tears electrons to create plasma. The Hall thruster uses magnetic fields of electricity to rip off electrons of a neutral gas to produce plasma. And the MPDT uses lithium gas and electric currents to produce magnetic fields to produce plasma. For the ion engine, get this in your notes, the ion engine had its earliest roots with the ideas of American rocketry pioneer Robert Goddard. Robert Goddard was an American physicist and inventor who is known as the father of modern rocketry. In 1907, Goddard proved that a rocket's thrust can propel it in a vacuum. In 1914, Goddard received 2 U.S. patents for liquid fuel rockets and for 2 to 3 stage rockets that use solid fuel. Goddard's many inventions were the basis upon which modern rocketry is based. Goddard's first successful rocket was launched on March 16, 1926, from a relative's farm in Auburn, Massachusetts. It was a liquid-fueled 10-foot rocket he called Nell. The flight lasted 2.5 seconds. The rocket flew a distance of 184 feet. In 1929, Goddard launched the first scientific payload that included a barometer and a camera aboard a rocket flight. Soon, Goddard moved to Roswell, New Mexico, where he developed more sophisticated multi-stage rockets, rockets with fins to steer them, a gyroscope device for rocket control in 1932, and supersonic rockets in 1935. In 1919, Goddard wrote a scientific article, A Method of Reaching Extreme Altitudes, which described a high-altitude rocket, which was a groundbreaking article, which was published in Smithsonian Report. Misunderstood completely, the New York Times newspaper ridiculed Goddard, stating that space travel was impossible and that Goddard seemed to lack the knowledge given out daily in high schools. The New York Times did not print a retraction until 3 days before man landed on the moon on July 17, 1969. Today, scientists know that to reach long distances in space, we not only need new technology, but we need better engines, such as plasma engines. This ends your lecture. Thank you.